So this is example 7.1, question D. Find the domain and range of the function y equals 2 on x plus 3. You should recognize that this function will exist everywhere for all values of x except when our denominator equals 0. So to find when the function doesn't exist, we let x plus 3 equals 0, so then x equals -3. Now that's pretty obvious. You can do that in your head, but later on when you're dealing with much more complicated functions, you will need to set the denominator equal to 0 and solve, perhaps using factorization or the quadratic formula or something like that. But the method is still the same. So that tells us that our domain is the set of all x such that x does not equal -3. And you can see that that's confirmed on the graph with the presence of the vertical asymptote at -3. With the range, we know that we've got a horizontal asymptote on the y-axis, so the range is simply the set of all y such that y does not equal 0. You can write them in interval notation too if you wish. So that would be x is an element of -infinity to -3 not included, or -3 not included to infinity not included. And the same with the range. I'm going to keep working with set notation rather than interval notation though. 7D, example 7.1, question E. So this is now question E. We've got 1 on √3 minus x, and we need to think about for what values of the function does this make sense. We know that the denominator can't equal 0, so we're going to have some sort of asymptote at when the square root of 3, when the square root of 3 minus x equals 0, we're going to have an asymptote of some description. It's going to be undefined. So if we just look at that, we can square both sides, and then x equals 3. If we just look at that, we've actually only considered half of the possibilities, because the other thing that we need to consider is that it's not only the denominator that equals 0 that's going to cause some problems. We know that there'll be an asymptote when the whole denominator equals 0. But we also know that 3 minus x, because it's under the square root sign, 3 minus x has to be greater than or equal to 0. We can't take the square root of something that's negative, so the thing under the square root sign, the 3 minus x, that itself has to be greater than or equal to 0. So in actual fact, what we need to do is deal with this inequality here, and we have then that 3 is greater than or equal to x. So x has to be less than 3. Think about it. If we've got x equal to 4, for example, we're going to have 1 over the square root of 3 minus 4, which is 1 over the square root of -1, which is when we end up with imaginary numbers. So be very, very careful when there's a square root in the denominator. And you can see that when this function is graphed, it does actually only exist for values of x down here that are less than 3. As soon as we end up above 3, the function doesn't exist, and you can see that the function does not exist in this region here. If you're not convinced that the function doesn't exist there, zoom right out on your calculator and you'll see that there is no second branch to that function. So for that one, our domain is going to be the set of all x such that x is less than or equal to 3. Our range, again, we can see from the graph, the range we have horizontal asymptote at y equals 0. So the range this time is going to be the set of all y such that y is greater than 0. Notice that it's greater than and not equal to, because there's nothing below the y-axis over here. Okay, so we need to be careful that we're specifying only that one little section. All right, the last one, if you're having a look at this, exactly the same principle applies. The function exists everywhere except for when the denominator equals 0. So when x squared minus 16 equals 0, you can factorise that using difference of two squares expansion. X plus 4, x minus 4 equals 0. Therefore, x equals plus or minus 4. Or you can just solve it via moving the 16 over and taking the square root. Either way, you can see that algebraically we've confirmed that we've got these asymptotes here at positive and negative 4. So our domain is going to be the set of all x such that x does not equal positive or negative 4. And we've got a horizontal asymptote that you can see on the graph. The range is, that should be equals the set of all y such that y does not equal 0. All right, just further down I've got a couple of slightly trickier examples. If we have a look at this one, we can check with our domain. Now, here we've got an x in the denominator. We've also got an x by itself over here. We need to consider the function as a whole. So, does the function ever not exist? And the answer is yes. The function will not exist when x equals 0 because we'll be trying to divide by 0. So if x equals 0, then we've got y equals 0 plus 1 on 0, and this 1 on 0 causes the whole thing to be undefined. So it doesn't matter if the denominator applies to the entire function or even just part of the function. If there is a denominator, the function will not exist when it equals 0. So, and that's confirmed on the graph. And the tip for new players is always graph these functions if you're not sure what they look like. So our domain is going to be the set of all x such that x,